Hello, class. This will be the last of the recorded lectures for section 5.2, which is polar graphing. And so this section is going to focus on the idea of symmetry in the polar coordinate system. Symmetry as a concept in math is super important. We talk about it quite a bit in the rectangular or Cartesian coordinate plane, where we have symmetry around the x-axis, symmetry around the y-axis, symmetry around the origin, which implies either even functions and odd functions with regards to the symmetry aspect of it. And so we're going to introduce you to this concept of symmetry in the polar coordinate system. You'll find that when you get to Calc 2, for some of you heading to second year calculus or second term calculus, you do a lot of transformations and you will get quite a bit into the polar coordinate system. So with that, let me pull up the definitions. Here we go. And so here are the definitions. And so we're going to talk about three different types of symmetry in the polar plane. The first one here, all the way to the left, is symmetry about the polar axis. And so the polar axis is this idea of R, where R is theta and minus theta. So you could see that idea. And the symmetry about the pole is the change of sign of R. And so R would go from positive and R is negative with the same theta. And then this one here is symmetry about the line theta equals pi over 2. Well, if you think about the theta equals pi over 2, that's kind of the y-axis aspect, right? And so you could see here, instead of different signs for theta, what are we doing? We're getting the difference between pi or 180 degrees. And so here's the definitions. And this is how you test for the three different symmetries. So the first one, polar equation is unchanged if you change theta to minus theta. And so that is implied that the graph is symmetric around the polar axis. If the equation is unchanged, when you replace R with minus R, it's symmetry around the pole. And then this is the weird one. If you change the equation, or if the equation is unchanged, if you replace theta with pi minus theta, then it's a symmetry around the vertical line, theta equals pi over 2, or the y-axis as I implied. And so let's take a look at a couple examples with regards to these three definitions. And so let's take this equation, for example. R equals, say, 2 cosine of theta. And let's take a look at the polar aspect of the symmetry, the polar axis. And so the idea is that what you want to do is you want to replace theta with minus theta. And the question is that if the equation stays the same, then it's symmetric around the polar axis. So here's where the symmetry properties come quite handy. So if you remember, cosine of minus theta equals cosine of theta. So you could rewrite it using the symmetry property, cosine of theta. So you could see these two are equal. And so it's symmetric around the polar axis. Let's do an example where it's not. So let's see here. Let's pick an orange equation here. Let's change it to sine, right? So remember that when you replace it, be R2, R equals to sine of minus theta. So in the symmetry property, remember minus, say sine of minus x equals minus sine of x. So this would imply R equals minus 2 sine of x, or sine of theta, excuse me. So you can see that these two values are not equal. And so in that case, that it is not symmetric around the polar axis. So moving on to the symmetry around the pole, where we're replacing r with minus r. I think this one is probably the easiest one. So if we go back to an equation that looks like this, all right, and we just say, okay, replace r with minus r, and you could see by definition, these two are opposites of one another, right? So this is not symmetric around the pole. But if you took an equation that looked like this, say it was r squared equals 4, or not, it doesn't have to be 4. There we go, 2 cosine theta. If you plug in r squared in this case with minus r and then squared, you could see now it ends up being the same equation. So the strategy here is if you don't have an r squared, you're pretty much out of luck. And so this one here, you see they are the same. So this is symmetric around the pole. Let's take a look at the last one, which would be the vertical line symmetry part of it. And let's take a look at a couple of equations. And this one's a little bit trickier. So let's take a look at this one, see what this one gives us. So say like you want to replace it with pi minus theta. So you have r equals 2 cosine of pi minus theta. And guess what? You could use the sum and difference formula now to figure out if this is symmetric or not. So how would you do that? Well, you have to get at the sum and difference. And if you look at the cosine, it would be 2, and whoops, yeah, then it would be cosine of pi, cosine of minus theta. And then it would be, since this is a minus, this would make this a plus. Sine of pi, sine of minus theta. And so if you look at this, sine of pi, right, is the same as sine of 0. And sine of pi and sine of 0 is 0, so this goes away. So if you look at what we have left, we have 2, and then we have cosine of pi, and we have cosine of minus theta. So this is the one that takes a little bit of work. Well, what's cosine of minus pi? Well, cosine of 0 is 1, so cosine of pi is minus 1, all right? And what does this equal? Well, by the symmetry property, what do we have? We have cosine and the minus, so that ends up being just cosine of theta. So you could see that it's not quite equal, right? They're opposites of one another. So this is not symmetric around theta equals pi over 2. Okay, so let's redo the calculation with a slightly different equation and show you how you do get symmetry. Wrong color. Try again. 2. So say we can make this 2 theta, instead of just theta. So again, let's use green and we'll replace it. So now it looks like cosine, and then we have, whoops. We have 2 times pi minus theta. So again, we look and we do a little bit of distributing, and we have 2 pi minus 2 theta. So again, if we use the addition, subtraction, or the sum difference formula, it would turn out to be cosine of 2 pi times cosine of minus 2 theta. And then there's a minus, so this would be a plus. Sine of 2 pi again, sine of 2 pi, sine of minus 2 theta. And again, sine of minus, or sine of 2 pi is 0. So this goes to 0. What? Whoops. I must be getting tired. This would be the last lecture of the day for me to record. Forgot my 2 here, right? So, what is cosine of 2 pi? Well, cosine of 2 pi is 1. And so if we rewrite this, this could look like this, cosine of minus 2 theta. And again, by the symmetry property, the minus goes away. Cosine ends up being 2 theta. And so you can see these two are equal. So this one is symmetric around the line pi equal, or the line theta equals pi over 2. So that ends the recorded lectures here for section 5.2, and this dealt with graphing in the polar coordinate system.